Marcus had been staring at the same screen for 6 hours. The AI had run its full diagnostic sweep, 14,000 network nodes, every firmware version, every patch level, every known vulnerability signature. It came back clean. No abnormalities, no threats, no reason to escalate. What Marcus didn't know, what the AI couldn't know, was that something had been living inside its network for 217 days. Today, we are going to talk about the firmware vulnerability that AI abnormality detection was never built to find, and about the human engineer who found it anyway. By doing something no algorithm can do, it got suspicious. In the last 5 years, enterprise networks have become too large for humans to monitor manually. Not too complex, not too technical, too large. A mid-sized bank today runs somewhere between 50,000 and 200,000 networked devices. A hospital system, more. A telecommunication carrier, millions. 90% of large enterprises now rely on AI for some form of network monitoring. By 2026, that number is expected to reach near universal adoption. And that makes sense. AI doesn't sleep. It doesn't miss alerts at 3 a.m. It can process telemetry from every device on the network simultaneously and flag abnormalities in milliseconds. So, IT teams trusted it reasonably, responsibly, the way you trust a smoke detector. You stop thinking about fire because the device is thinking for you. But there is a class of threats the smoke detector was never designed to detect. Not because the AI failed, not because the engineers who built it were careless, because the threat lives in a layer the AI was never told to watch. AI in networking is one of the genuine engineering achievements of the last decade. It can inspect millions of packets per second for known threat signatures. It can correlate abnormalities across tens of thousands of devices simultaneously. It can detect when a device starts behaving outside its baseline. More traffic, unusual ports, unexpected connection patterns. Cisco's AI-driven threat detection, Juniper's Mist AI, Arista's Cloud Vision. These platforms catch things that would have taken a human analyst weeks to piece together manually, and they catch them in seconds. That is not a small thing, that is a remarkable thing. Firmware is a code bound directly onto hardware. It runs before the operating system. It runs before any software the AI can see. When a device boots, firmware is the first thing that executes. It initializes the hardware. It hands control to the operating system. And then it sits there, invisible, persistent, and in most enterprise environments, unmonitored. Most AI network monitoring tools operate at the traffic level. They watch what moves across the network. They watch what the operating system reports. They don't watch what the firmware is doing, because firmware doesn't produce the kind of result that an AI abnormality detection was trained on. The most secure networks in the world right now are not AI only. They are not human only. They are layered. AI monitors the traffic layer. Humans watch for what doesn't feel right, even when they can't immediately say why. And it is precisely that second capability, the instinct, the context, the suspicion that something is off, even when the logs say clean, that machines have not learned to replicate. Marcus have been working that network for 4 years. It knew its rhythms the way a surgeon knows a patient. And something was wrong. He just couldn't prove it yet. Marcus ran the standard diagnosis suite first, not because he thought he would find anything. He had already run it twice, but because he needed to document that he had. When you're about to tell your security team that the AI is wrong, you need a paper trail showing you started where everyone else would start. Everything came back clean. He then pulled the device logs for the past 30 days across the 7 switches in the affected segment. Standard traffic patterns, normal CPU cycles, no unauthorized access attempts, nothing the AI hadn't already cleared. But here is what Marcus noticed, and this is the part no algorithm had flagged. The boot times were wrong. 6 of the 7 switches in that segment booted in the expected window, between 4.2 and 4.6 seconds. One of them was booting in 4.61 seconds, consistently, every restart for the past 3 months. That switch took 11 milliseconds, longer than it ever had before. 11 milliseconds, not enough to trigger an alert, not enough to flag in any anomaly detection system, not enough for any human to notice unless they were specifically looking at boot time baselines and comparing them against historical norms from the same device. Marcus was looking because 4 years of watching the same network teaches you what normal feels like, and this didn't feel normal. He requested a firmware integrity check against the manufacturer's known good baseline. It was not a standard part of the security workflow. His manager pushed back. The AI had already cleared the network. Marcus made the case for 4 hours before he got approval. The check took 11 minutes. He requested a firmware integrity check against the manufacturer's known good baseline. It was not a standard part of the security workflow. His manager pushed back. The AI had already cleared the network. Marcus made the case for 4 hours before he got approval. The check took 11 minutes. The firmware on that switch had been modified. A small persistent model, a few kilobytes, had been inserted into the boot sequence. It executed before the operating system loaded. It was invisible to every monitoring tool running above it, and it had been there, quiet and patient, for 217 days. The AI never flagged it because it never produced the kind of traffic abnormality the AI was trained to catch. It was patient, it waited. The human caught it because it noticed 11 milliseconds. What Marcus did is not what engineers are being trained out of doing. It is what engineers need to be trained into doing better. It knew the baseline. It noticed the deviation. It trusted the deviation over the clean report. It made the case for investigation when the institutional incentive was to trust the AI and move on. That is not a legacy skill. That is a skill that becomes more important as AI monitors more of the surface, because the surface AI monitors will always have edges, and the threats that understand AI will always look for that edges. AI abnormality detection is trained on known threat patterns. It is extraordinarily good at recognizing variations of things it has seen before, but a sophisticated firmware implant that produces no abnormality traffic, generates no unusual log entries, and changes nothing visible above the firmware layer. That is not a variation of something the model was trained on. It is a new shape of threat, and new shapes of threat are caught by pattern recognition of a different kind, the human kind. The kind that notices when something has changed without being able to immediately articulate what changed or why it matters. 217 days, that is how long this threat operated inside a monitored, AI-protected, enterprise-grade network. The question is not whether AI should be monitoring your network, it should be. The question is what humans are doing while the AI monitors, and whether they still have the skills to catch what the AI cannot. The most dangerous network is not the one with no AI. It is the one with AI and no humans who know how to question it. The networks of 2030 would be larger, faster, and more automated than anything Marcus was managing in that control room. They will also be more dependent on AI than anything currently deployed, which means the firmware layer and every other layer that AI was not specifically trained to watch will become a larger and more valuable target for the threats that understand how AI works. Gartner projects that by 2027, firmware attacks will be among the top 3 vectors for sophisticated enterprise breaches, especially because they operate below the monitoring layer most organizations have invested in. The roles that will matter are not the ones that know how to run the AI tools. Those are table stakers. The roles that will matter are the ones that know what the AI tools are not watching. AI network supervisors who define the monitoring boundaries, firmware security specialists who own the layer beneath the AI visibility, threat hunters who do what Marcus did, spend time looking at numbers they feel wrong, even when the system says they are right. These are not future jobs. Several of them have job posting right now. The question is whether you are building towards them or away from them. Marcus filed this report at 2:17 in the morning. The threat was isolated, the firmware was restored, and the affected switch was pulled from the network pending a full security review. He never made headlines. His name never appeared in the press release. The organization he protected never publicly acknowledged that a sophisticated firmware implant had been living in that infrastructure for 7 months. That is how most of this work goes. AI didn't catch the threat. Marcus caught it. And Marcus caught it because he never stopped treating the claim report as a ceiling on what is possible, only as a floor for where to keep looking. The AI found nothing. It found everything. The firmware no AI was ever meant to find, found by a human who refused to stop looking. If Marcus' story resonated with you, I want to know something. In the comments below, what layer of your network are you most confident the AI is not watching? What's your blind spot? Because I bet most of you have one, and the engineers who know where theirs is are the ones who matter most in the next 5 years. Next week, I'm going into a case that makes this one look small. An AI routing system that silently rerouted 40% of enterprise traffic, and the team that discovered it only because a human engineer noticed that 2 sites were talking to each other in a way they've never had before. Subscribe so you are there when it drops. And if this gave you something to think about, share it with the engineer on your team who think needs to hear it most.